Okay, so yeah, I want to talk to you today about designing programs and designing two kinds of programs. One is a language, a programming, a language processor, a compiler or something that supports functional dependencies, and one is about the kind of program that uses functional dependencies. So language and program design for functional dependencies. But functional dependencies have, well, frankly, gotten a bit of a bad rap over the last few years. There's been a bit of negative PR, and you know, I think the market is, the bottom is falling out of the market. They've been beaten up a little bit. So maybe what I'm really here to do today is to tell you that you still can depend on functional dependencies. Well, I'm going to start. Some of my colleagues tell me that I've been type-classed. And I'm going to start, as I often do, by talking about type classes very briefly. And the view of type classes that I want to be focusing on today is that a type class is a set of types, it's instances. So I didn't even bother to show you the instance declarations, but the eq type class is int and bool and so on, and lists of equality types and pairs of equality types, and so on. And this is a very appealing and nice way, I think about a type class. Of course, we're also interested quite often in the implementations of the overloaded operators, but I want to just focus primarily on the instances. And one of the reasons I want to do that is because I want to talk about multiple parameter classes. Multiple parameter classes were anticipated in the very first paper, Wadler and Bloch in '89, suggesting that multiple parameter classes might well be useful. And a multiple parameter class, if a single parameter class is just a set, a multiple parameter class is on types. And it doesn't matter whether you choose to express that relation by a bunch of instance declarations, or as a set of tuples on types, or in a form that I find useful to, especially for what I want to talk to you about today, to think about it as a table of types, something in this form. But they're all completely interchangeable. It's just a matter of presentation how I show these to you. Now, one of the things about multi-parameter type classes is that we can sometimes exhibit some beautiful relationships. One of my favourites, one of the first sort of successful uses of multi-parameter type classes was in dealing with things like the state monad class here, a two-parameter class that relates state types to monads. And this is a class in which you can sort of say, this monad has a state component of that particular state type S. And this is a beautiful application for a many-to-many relation. Just what we need here, because multiple monads, of course, can have an integer state component, so that makes sense in that way. But also, a single monad can have multiple state components. And so this many-to-many relationship is beautiful. It's exactly the right match. And this was actually one of the first examples, as I say, where multi-parameter type classes really worked. And it's kind of ironic to me today that if you look at the libraries, this has a functional dependency on it, which is completely unnecessary and gratuitous in my opinion. But anyway, this is a nice example where multi-parameter classes work. But those of you who were there at the early days know the excitement and the anticipation as we waited for the first implementations of type classes was soon beaten into frustration and madness as we discovered that many of the original applications didn't work, like the plus example that I gave you before. Now, the plus example, what I mean by it didn't work, I mean it just sort of kind of blew up into much more complex and difficult, awkward to work with programs than we expected. So here's a simple function that adds three values, x, y, and z together, just by adding the x to the sum of the y and the z. And it's a nice, simple function, but if you try and figure out what its type should be, it's this kind of fairly complicated looking thing, and actually, this is not such a complicated example. We can work out what's going on here fairly easily, but it turns out that this time, I think it's still kind of hard to read, written in this notation, and worse still, it's semantically ambiguous. If you feed this into just a regular Haskell type checker circa 1990 or something like around then, it's going to complain that this is ambiguous. And the problem, I think, in both these cases, is that D variable floating around there in the context. There's this magic D that's sort of trying to name some type, but that type doesn't appear anywhere else except in the context. It doesn't appear elsewhere in the type. That's why it's ambiguous. I think that's also one of the reasons why it's hard to read. So now, I'm going to talk about functional dependencies. I've been hiding away for 8 years, and now I'm going to finally talk about functional dependencies. And I'm going to tell you about functional dependencies by just introducing you, reminding you of the database connection here. A program in Haskell defines a collection of classes. And each class, with the view I've been promoting here, corresponds to a relation. Even a single parameter type class is just a relation, it's just a set. Those are the same thing in that case. A collection of named relations. That sounds like a concept I've heard about before in computer science. It's a concept called a database. It's a relational database. And so the key insight here is that these programs, these sets of instances, can be viewed and manipulated as a relational database. And the benefit of that is that we can then leverage tools and results and ideas from database theory to specify and to use multi-parameter type classes more effectively. So in the case of the plus class that I mentioned previously, here's that table I showed you before, and a database person will look at this and go, this appears to have a functional dependency, meaning that if you know the values of the first two columns, the A and B, then the third column, the C column, is uniquely determined in that case. Now, this is not something that a system can decide automatically for you. This is something that only the designer can know for sure, that there really is a functional dependency. In fact, there are other possibilities that we could try to infer from this table. But this one actually makes sense. If you give me the two inputs to a plus, I think I can probably guess what kind of output I might want from that. So a designer has this intuition about properties of the relation. How can they express that? It used to be that there was no way to express that in Haskell. I guess officially there is still no way to express that in Haskell 98. But what we've been able to do with functional dependencies is put annotations into the programs that let you characterize the relation more precisely. So here's the class I had before, and think about a functional dependency as being like a type for a relation. That's how database folks think about it. A functional dependency is just a sort of refinement on the type, clarifying the type. Here, this is the annotation that says A and B uniquely determine C. And there's a price to pay for this. We don't get anything quite for free here. The price is that now the compiler has to do some extra checking to make sure that the instances that you provide in the program really do conform to this dependency. You have to check that A and B really do uniquely determine C in every case. But there's a payback too. Extra information is provided through this mechanism, and we can use that extra information during type inference to eliminate some of the ambiguities and to infer more accurate, or maybe you could just say more readable types. And I won't labour that, but I think you've probably all seen good examples showing that kind of thing. Okay, well this was some time ago, and the years have passed. That seems to be a common theme for me, doesn't it? Years have passed. And initially, I had fun with functional dependencies. But I began to sort of see some seeds of unrest with Matthias Neubauer and colleagues exploring a functional notation for functional dependencies. Manuel and colleagues, associated types with class, index type families, and I knew lightheartedly, I know, I'm sure, but death to functional dependencies. Maybe I thought it's time for me to speak up briefly a bit. So what went wrong? I thought about this. There was this mechanism, once loved, praised, embraced, and adopted, was now being reviled, blamed, rejected, and shunned. Well, buggy implementations and oversights in the original paper probably didn't help. But as I've analysed it, I've come to realise that there were three reasons for it being shunned. I call them the three shuns. One of those was foundations, education, and finally one of them was notation. So let me talk briefly about each of those three shuns. Foundations. So for me, the foundations of functional dependencies are database theory and improvement. And that's where it comes from. That's what the inspiration was. That's what I've used as the foundations. But I've found that users don't necessarily know about or understand these topics, and that users may not believe that they are relevant, even if they do understand these topics. So the conclusion here is that I think we need to do a better job in explaining, illustrating, and showing the relevance of those foundations more clearly. This is a lesson that I take away from this experience here. And one of the things I've done is I've actually put in the paper here, put some appendices that actually go into some detail in the paper talking about each of these two topics to try and make that paper a little bit more self-contained. I discovered that the original FundDepth paper, if I formatted it according to the same format as the format we have here, it's 6 pages instead of 12. So I just didn't have room for it before. That's my excuse. Now, education is the second of the shuns, and we find here that users may not know how to use functional dependencies effectively. For example, to decide, are they appropriate here? Maybe not, in the case of the state monad class earlier. Or to understand what makes a good design and what doesn't. And also to detect symptoms of a bad design. And so here the conclusion is, I think we need to provide guidelines to document good design patterns, and to do this in a way that targets developers as well as researchers. I don't think the paper I've written, I don't think the paper in the proceedings here is really beautifully targeted at the developer community, and we need to make sure that some of these ideas are positioned for developers as well as just researchers. And then the third of the shuns, the notation. Users struggle with awkward notation. Before are not easy to read or understand, and it gets worse with bigger examples. And so the conclusion I have here is that, yeah, I can't agree more with you, that we need a better notation. So that's my little prelude, and now I'm going to do two things. One about the language design and one about using these things, so the design of functional dependencies in programs. And the first thing I want to talk about in the language design is functional notation. What I'm actually going to share with you here was originally described in a paper with Yavor and myself 2 years ago, but I think a lot of it got lost at the time because that paper's primary focus was about memory areas, the kind of systems Haskell stuff that I was talking about yesterday. So here's the idea for functional notation. It's a very simple idea that gives us a nice notation for relatively low cost. Suppose that you've got a predicate x, y on types, so it's a two-parameter class in other words, and the y is functionally dependent on x. What I'm going to let you do is I'm going to let you write cx, a partially applied type class if you like, for the type y. That's the name of the type y. If there is one, this is a relation, it may not be defined, but if there is such a type y, we'll write that as cx. Concretely, what this corresponds to is a piece of syntactic sugar. If you see c, with the class C applied to a single argument s in a type, what you do is you replace that occurrence, cs, with a fresh type variable, and you add a constraint, csa, to the beginning of the type. If you like, I'm not so sure about this one, but if you like, you can push it even a little bit further, and you can even use a notation for predicates that actually inserts an equal sign just before the last argument there. So cs equals a could be taken to mean a functional dependency on this class that c determines a. Okay, so an example, +3 is the one I showed you before. Here's the type of +3, but if you look at these types now, D, you can see D is just the sum of B and C. So I can just replace it this way, get rid of the D and replace it with plus B and C. And now in the context I see, well, E is equal to all this plus of A plus of B, C and so on, and so we can replace that. And so now what we get is a type for +3 that says it takes an A, a B and a C and gives me back a plus of A to a plus of B and a C. And I don't know, but I think that type looks much nicer. Okay. The canonical example in this area is collections, so let me just talk about collections briefly. Here's the element class. A element class, C is a collection and E is the type of elements. And you give me a collection that uniquely determines the type of elements. We have a function for inserting an element into a collection and getting back a collection, and a way of extracting from a collection a list of its elements. A very simple little element class here. Okay, so the types of insert and toList can be written in this standard form. Creation, you can write in this way. Insert takes an element of C to C and gives me back a C. And toList takes a C, a collection, and gives me back an element of C. And that's, you can see, definitely shorter here, and perhaps more intuitive, more easier to see what's going on. For those of you that prefer functional notation in your types, there's more functions here and fewer relations to be worrying about. Some nicer properties as well. If you think about sort of just to expand this a little bit, here's the insert function that inserts two values, x and y, two elements of type C, two elements of the collection C into the collection C and give me back another collection C as a result. So if we look at the inferred type for this, actually we're just expanding the type, you'll see, well, LMC would replace the first LMC with a variable A and the second LMC with a variable B, and we get this type. That looks a little bit odd. That doesn't look quite what we would like, because we expect there to be uniquely determined type for every collection. But in fact, that's not a problem, because of the functional dependency, we can be sure that A is equal to B, and so we can actually simplify the inferred type of insert too, just as shown there. Okay. It turns out that type synonyms, a feature that's been in the language for a long time, are just really a special case of this mechanism. If you have a type synonym type T of A equals some type T, you can actually just replace that with a class T, which now has one extra argument, T of AB, with a dependency that A determines B, and just a single instance T, A, T. And obviously this generalizes if you have multiple arguments for the type synonym as well. So it's actually quite a familiar mechanism, really. Okay. Just one final little example here, index type families. So here's the add type family. I think I've got this right. We're declaring the add function that takes two arguments A and B, and the two sort of piano arithmetic rules that define what it is to add the successor of something to a number and the zero to a number. And if we just change type family to class and replace type instance with instance, using the notation I described here, I guess I may use the equal symbol here just to further emphasize the similarity, we get down to the same declaration, the same syntax, by just using this mechanism. The type classes we already have, plus this little notational trick. So what we have here is functional notation, a more palatable, much more appealing notation, almost for free. This functional notation is within reach. It just requires a simple syntactic transformation, something that you can almost do in the parser, maybe not quite, but something you can do at the front end, and it doesn't change the underlying mechanism. It doesn't change the type system or those parts of the system in any fundamental way. This is about presentation. This is about how you read and show types to the user. It's not about fundamental change. It's, as I say, similar to the treatment of type synonyms in that you have to have the appropriate number of arguments. And if you would like to see more details, chapter 7, something like that, is where you'll find this in Yava's dissertation. That's a good place to look for that. Just as a little aside, before I move on to my second topic, it turns out that this notational abbreviation I've been showing you doesn't actually have anything to do with functional dependencies. It can be completely decoupled and separated from functional dependencies. You could say if CXY is a predicate, anytime you write CS, only one argument, replace that with a fresh type variable and add something to the context. So that's, and notice no mention of functional dependencies in that constraint. So let me show you, it's maybe a little hard to see what that looks like, so let me show you some old friends in new clothes, dressed up using this mechanism. Here are some types. Show is a function of type show to string. From integral, it's just integral to none. And my favourite actually is the lift one down here. Monad M implies an M of A to a monad trans M of A. Well, monad trans is actually a class there, but it's being partially applied, and we're actually going to get back the fresh variable. So we get shorter types like this. I don't know that this is a good idea. It's kind of interesting, it's kind of curious, but it's kind of fun. Anyway, don't throw away your relational notation just yet, is my final comment on this before I move on to the next topic. We still need relational notation from time to time. Here's the element class, slightly simplified, an example we've seen earlier in the week, inserting the character X into some unknown collection. Now, how can I find a type for that function? What would the type be? The trouble with this example is that we can't be sure exactly what the type will be. All we know is we're going to deal with a collection that contains characters. We don't know anything more about the collection type. So using the sort of standard mechanisms, it's just this type here. LMC char implies C to C. We just take a collection and give you back a collection, so long as that collection contains characters. The point is, though, that whatever you do, some kind of relational notation is needed here, because the element type is not a function of the, the collection is not a function of the element type. And so some kind of relational notation is needed. If you don't have relational if you don't have a relational mechanism, you won't be able to type check this. So what we saw the other day, actually, Monday I guess it was, in Tom's talk, is a way of solving this by introducing equality constraints. So in fact, the type, because it distinguishes type families and classes, introduces two constraints here. One to say that C must be a collection, and the other to say the element type of C must be the character type. And this is much more powerful, and, but also I think much more complicated than the mechanisms that we need, at least for type functions. So this full power doesn't seem to be necessary, at least for dealing with type functions. This isn't to say that the mechanisms of equality constraints won't be useful elsewhere for GAETs, but in terms of notation, we don't seem to need the full power of equality constraints for this part of the system. Okay, now I'm going to talk about designing programs that use functional dependencies. I'm going to talk about leveraging database theory. And at this point, you're saying, Mark, you can't be serious, can you? All this idea about using databases with functional programs. What are you talking about? It's just not normal. Well, so if you look at the code for a well-known parser library, parsex 3.00, they generalize this so that you could talk about streams, arbitrary streams S, being pulled in through monads M with tokens of type T. And this is nicely generalized, the combinators work on this nice general model, and you can see there's a functional dependency here that says the stream type uniquely determines the token type. Okay, well, so questions come up. Is this a good design? Is it general? Is it flexible? Is it extensible? And, well, some people I know who work in refactoring have this notion of smell detection when they're looking for possible problems in the program. Something about this program doesn't quite smell right to me, because if you look at examples like there's the many combinator, but it has this T parameter that's not used. It's actually okay, we don't have an ambiguity because of the functional dependency, but it just doesn't quite feel quite right. And then there's down here in the token function, we've got this fixed monad down here, rather than some kind of general monad. It's specified to this, hardwired to this particular monad. Okay, well, database folks have thought about this kind of problem. Here's a table telling you where various employees live and the modes of transport that they use to get to work. And this is one way of capturing the data, but it's a little bit awkward, because well, it allows, for example, for me to have Alice living in 2 different places if I'm not very careful about how I update the table. It doesn't allow me to add a new employee unless I know both their residence and their transport. So this kind of, these are called anomalies in database design. But what we can see, looking at this with our functional programming eyes, is the functional dependency. That every employee uniquely determines a residence. This is a functional dependency. And in cases like this, those database folks have a process of normalization where they can suggest, well, maybe you should break this table down into 2 pieces. One that captures the mapping from employees to residents, and one, a separate one, that captures the relation between employees and transport. And you can know the original relation as a join of these 2 tables here. This decomposition helps to avoid anomalies and eliminate consistency, redundancy issues, and increases the flexibility. I'm not saying you have to normalize, database folks don't always normalize, but this is often a good thing to do. So if we normalize parsec, we break it into 2 classes. One that has the functional dependency for tokens, and one that doesn't for stream, that is just the purely relational part. And you can fill in the rest of the instances. I won't go through that, just wanted to show you that it can be done. And then we go back to the functions I looked at previously, and now the issues have been resolved. Now the many function purely is polymorphic in the stream and the monad, but we don't have to worry about the token type. It's not relevant for that function. And the token function can be described in this way. It's only using the top class this time. And if you don't like the top ST notation, you can simply inline it and use the functional notation I showed you earlier and write it this way. Okay. So what does this tell us? It tells us, I think, that functional dependencies provide a powerful tool for understanding and potentially improving design. They do allow us to create bad designs. So everybody who doesn't like functional dependencies, you can latch onto this. But on the other hand, well, even more, you couldn't make those designs if you only had type functions, because you couldn't have written that dependency I showed you previously with just type functions. But on the other hand, a different perspective is that functional dependencies allow us to create more designs. And some of them might be bad, but some of them might be more awkward to express if we had to do it using type functions. We actually saw this twice in the first 3 talks today, classes of this kind, dual AB, where you had a bijection going backwards and forwards between these things. And it is possible to capture that using type functions, but it's a little bit more awkward. So what we're really looking at here is an old debate, whether you're thinking about having functional dependencies or not, an old debate, where do you draw the line between protecting and empowering programs, protecting them from shooting themselves in the foot and empowering them to do interesting and maybe crazy things. There's actually a whole bunch more. Okay. Well, there's a whole bunch more in database theory that would be good to look at. Okay. So, closing thoughts. One thing I want to say is caution. We've developed over 20 years strong intuitions for types like this fully polymorphic type that will work for any A. Any of the proposals for functional notation we have, the one I've talked about, the one that others have talked about, will break. Because this function now, it translates potentially into something like this, and it could be overloaded, partial, and even ambiguous. So that's a real sort of shocking problem. It's something we will have to adjust the way we think about Haskell programs. For systems Haskell, what I talked about yesterday, we're looking at, as those of you who are systems-oriented dialect of Haskell, and will it have type classes, will it have function dependencies, will it have type functions? These are, to some degree, open questions for us at the moment. We do know that in Hobbit, Yarl's prototype, function dependencies weren't enough for everything we need to do. We needed some other kinds of improvement, stronger kinds of improvement. But one thing that we do have is that sort of hedging our bets, building a type inference engine now that supports kinds, qualified types, and improvement in a general way is going to let us go with any of these options as we move forward. The other thing is, for standard Haskell, is it too late to say functional dependencies? They're head on the chopping block already. Well, personally, there are strong reasons, I think, to retain relations with functional dependencies and the functional notation that I described today. Some of those reasons include the immediate integration with classes and kinds and superclasses. You don't have to describe how these mechanisms interact. It's all just one mechanism. You have full backwards compatibility. Somebody doesn't have to go through and make the change. I've seen that several times. I'm porting my code to TypeFamily. You just use it now and you can start moving to the functional notation as you wish. And then the relational notation, I think, is preferable in some cases. It would be a shame to lose that, but the functional notation is available when you want it. My final thought, though, is that with all this, there are still some issues that we need to work on. And one of those, I think we do still need to work on the education in sharing some of these issues, sharing some of these principles for design. That's it. Thank you.
Mentioned that you think that in the monads library, for example, for monad state, there shouldn't be a function dependency of the state type on monad type constructor. I'm wondering, so my personal understanding is that it's supposed to prevent overlapping instances. Now, of course, in most cases of actual use, it's not going to actually be a problem to have because we never put, we never put two pieces of int state in the same monad. But of course, so I guess the final question is: do you think we should actually just follow the database or data log traditional way and add backtracking to the search for instances? Maybe not backtracking.
So I guess there are two questions there. So the first thing is I've used state monads, or monads, composite monads that do have multiple components of the same state type. And maybe that's bad style for me, so those examples prevent me from. I can't use those examples with the MTL library. So, but that's one thing. The other thing is the full backtracking prologue or data log, whatever. The challenge there is that we want to be able to ensure that we have, for semantic consistency, a unique implementation of any overloaded operator. And so the challenge is if you have a kind of more complicated search process, it's much harder to distinguish that. So we have these kind of rules that just look at the heads of instance declarations.
Okay, a few questions. Just a remark. First of all, probably a better example for relational notation is kind of pulled out from your example for plus. As you know, in your example for plus, the first two arguments determine the third. But it's relatively easy to write a plus where any two arguments determine the third. And then it actually gets interesting. And ironically, as a matter of fact, we use this plus operator addition as well as multiplication revocation and deletion and so forth, where every two returns a third. And it's implemented something that you on the last but one slide said that you have it.
This is what you're looking for down here, the added 3 different.
Yes, so we implemented that, and you claimed in 2006, I think, in a Haskell workshop that you cannot implement arithmetic and strong type memory errors in Haskell, and as you know that we actually can do all your examples in Haskell. So perhaps you even underestimated functional dependencies, you can actually do more than that you thought that we can.
So I think there's a. So you posted something on the mailing list about this the other day. I hadn't had a chance to respond, but so we're here. It's never been a surprise to me that we had essentially the right type theoretic engine already inside Haskell to do these things. The type area stuff is about doing that in a way that throws out some of the primitives like peek and poke and so on that are unsafe, and also about finding a notation that makes it more palatable for people to use. So it's like saying, to some degree, I'm going to exaggerate a little bit, but it's a little bit like saying I can code up this program with a Turing machine, so I don't need anything but a Turing machine. So there's a little bit more to it than just that.
But the point of view of the arithmetic, that all the arithmetic can be done in types. So, and for some of them, it fully requires relational notation. So that's the point.
Yes.
So that's the example where relational notation is really important because, for these things, add and plus and other things.
Well, so those who work on type functions assure me, and I believe them, that you don't have to use a relational notation. There's a translation that goes backwards and forwards between the two. So you could do everything with the functional notation, but for me, subjectively, that seems more awkward. But
can you say something more about the expressivity? Because is this on? Can you say something more about relative expressivity? Because it seems that seems a reasonably obvious syntactic translation, but things like the coverage condition and the restriction side of it, I find very confusing. So I don't know what I can do with what.
I think these two mechanisms are really quite interchangeable. I don't have a formal proof for that, but my sense is that if you're just talking about type functions in Haskell 98 kind of language, they're really pretty much interchangeable. One of the things, so when Tom presented the conditions, so I've never been worried about termination of my type checker. So I don't think Hugs has terminated on me, failed to terminate on me for a long time, but I've never been worried about that. But I would imagine that the conditions that Tom presented for guaranteeing termination could be mapped to the functional dependency. I haven't done that. But I think there's likely to be, so in areas that I think I've neglected on the functional dependencies side, I think there are results on the type function side that we can borrow and move those things backwards and forwards. The coverage condition, whatever, was presented in a weak form in the original paper, which I think has caused some confusion as well. And there's a sort of a unified, I think there's a general agreement on what that can look like that covers each of these systems. So I think, we're really at this level talking about what notation is best to present to the users in some ways, and I don't think there's a big difference in expressivity. That may change, maybe, I don't know. I was going to say that may change when we add extra features to the language, but I'm not sure I believe that either. So.
Any more questions? Are we done? You're all right. Pass this down. Pass this down.
So part of the difference with the functional approach, type functions, that's the word, is power. And the impression I have is that the type functions do let you do things that you can't with functional dependencies. So for instance, the type preserving compiler that we saw works with type functions. I'm not sure it would work with what you've shown here today.
I haven't tried it, but I believe it's I haven't seen anything to tell me that it wouldn't work.
I tried something similar and couldn't get it to work. Something with my own side.
So I think I maybe know why. So yes, I think it's to do with the interaction with JVT. So Mark, in your paper, you say explicitly that you not considered interaction with JVT.
That's right. Yeah.
And I do think that one of the things that has driven us to the fairly long diversion into type functions and equality predicates that we've taken has been precisely to try and really nail down the interaction of all these type equalities with GATs. And that was, I think, essentially in type preserving compiler. Certainly GAT's implementation of functional dependencies, and I believe Hugs, is completely inadequate the implementation is completely inadequate to deal with the interaction of functional dependencies and GADTs, and we need completely to that interaction. I don't even know, and we don't have a formal theory for what it would mean yet. I mean, it's because you haven't thought about it, and nobody has. So there's a big unknown area, which I think for the equality predicate and type function stuff, we've worked hard to nail down.
So I guess three things. One, I'd forgotten that the GADTs are used in that program. Of course they are now, and I haven't explored this area with GADTs at all. Second thing I think is the type equality stuff is really about the mechanism that will be used. To some degree, it will perhaps show through to the user inevitably, but it's one of the external mechanisms that will be used. It's less to do with what it would look like on the surface. And the third thing I wanted to say here is I don't trust the implementation of hugs to tell me reliably, or GHC, although I have less. I don't trust the implementations to tell me reliably what functional dependencies can or can't do. I think I know of some bugs, some infelicities in the design, some mismatches between the theory and the practice. There are bugs in those systems that we need to fix if we want to give a true picture of what we can and can't do.
Thank you very much.